Welcome to this lecture. Now, we have seen various basic parameters of antennas. Today, we will see a really useful antenna. Already, we have seen the elemental antenna, that is Hertzian dipole or current element, but we have seen that time that current element is not a practical antenna because of several reasons. One was that its length is infinitesimal, so it is very small, and for that we have seen that its radiation resistance is very small. So, if we want to have a sizable amount of power radiated, we need to have a huge current in the antenna, which is not practical. Also, we have seen that in the current element, the current is constant throughout. Now, that is not a physical approximation, because if we look at any length of an antenna and if throughout the current is constant, that means at the end points also the current is non-zero, but immediately after that there is free space. So, conduction current cannot be present there. So, where that current goes? Now, we know that it goes to the conduction current gets transferred to displacement current, but if throughout we assume there is same current, then there is a severe discontinuity there. So, it is not feasible to have a practical thing, but we have already noted that current element is as an source of antenna, it shows all the properties that any other complicated antenna have, particularly the far field structure, various other properties, etc. So, that is why we have seen that. Today we will see a really useful wire antenna. First we are starting with wire antennas, which are wires, a type of wire structures. That means it has length, it does not have any width ideally. So, the two such examples today we will see one by one. The first one you can see in the view graph, that the first one will see the dipole antenna, which everywhere you will be seeing that there are these dipole antenna. It is very popular, it is very useful. So, it is a length L. So, it is symmetrical, it is have two such parts, each part is having L by 2. These are called poles of the antenna. So, this is the upper pole, this is the lower pole, and between them there is a source, AC voltage source, which is there between the two antennas. This is the structure of dipole. Now, sometimes particularly at lower frequencies, if this length is quite high, if such a high length is not permissible, another variety of this dipole antenna, which is called monopole antenna, is also there. So, in this case the source is there, and from the source there is only a single pole, the upper pole is there, the lower pole is not there. So, how would they make it? So, there should be a infinite ground plane, infinite perfect ground plane, so that by image theory it is the dipole. So, if we place a ground plane here, then we need not have the lower pole. So, this is called a monopole antenna of height h. Okay. So, these two structure today we will try to analyze. First, we will start with the dipole. Now, in case of dipole, how to analyze? First, obviously, we have noted that any antenna, if we want to find its fields radiated, we want to find the current distribution, because from the current distribution, by solving Maxwell's equation, we can find the fields. Now, so that means the first job we will have to have what is the conduction current that is flowing on the antenna. Now, here we will have to have a guess. You see, this is a long antenna. So, antenna is like this. So, we know that physically the current, actually we are feeding here, that means the current may be maximum here, but it should go to 0 at the ends. So, what can be the structure of that? To understand that, we take the help of a transmission line, because we have already seen the transmission line. So, let us see a transmission line which is fed and an open circuit transmission line. So, in a transmission line we have already seen in the EM theory classes that if I have a current I z, obviously here the radiation is taking place. So, this current, conduction current is getting converted to displacement current, and the return current is like this, and we know how this current is distributed. So, since this is an open circuit, so here the current should be 0, the voltage is maximum. So, current has a minimum here, that means we have a distribution like this, that we have seen in case of the when we have seen a thing. So, that you can see in the view graph that the current distribution if I plot, that means I z if I plot as a function of z, it is something like a sinusoidal. Now, suppose I change this to transmission line, their internal angle or their flare is increased, then also it is reasonable that nothing physically is getting changed. So, the current distribution will be something like this, because the logic from which we have said that okay, it should be 0 here, that is still remaining. And then if we just make it like this straight to, then also this should be the current distribution. And people have also measured and found that the current on a long dipole antenna, that is indeed something like this, that at the end it goes to 0, at the two ends of the two poles it goes to 0, and in between there is a sinusoidal distribution. So, we can now say that we know that what is the current distribution here, and from that we can solve. But that means if I know the current distribution, from the Maxwell's equation we have seen in the first classes, that how to write the vector potential, magnetic vector potential, and from that how we can find the electric field and magnetic field. But if you can want to do this, which we have done for current element, but in this case if we want to do that, it will be a tough job, there will be some integrals which we will not be able to do. So, we will take a simplifying route. We have already said that we are mainly interested in the far field of the antenna. So, we can say that the far field of the antenna, if we are interested, then what we will do, we will actually break this. Suppose this is the current distribution. Now, we will break this whole dipole into small infinitesimal current element of length dj dash. So, small current element will do. That means, here if we say we will break this into, suppose this is a current element, this is a current element, this is a current element. So, this is one, this is one, this is one, like that, and here also we will make that. Now, I know the current distribution. So, I know the value here. So, between these two, suppose if this was the current distribution here. So, for this one I will assume that this is the constant value. Similarly, for the next one I will assume this is the constant current value, and then I will go as if these are all current elements. So, this individual current element, now I know the result, that at a distance point p. So, again we can see at the view graph that that at this point what is the field, at least for if P is in the far field, what is the far field here I know, and then I can then I go to the next one, and so the total field here will be superposition of all these fields. So, that means basically this whole long dipole that I can break into current elements distributed throughout its length, and each current element will have a current value that I know from the assumed current distribution. Then I will be finding the what is the field at P, then I will have a superposition of those fields and I will find out. So, to do that we need to just modify our some terminology. One thing is, now you see we will have to have in the spherical coordinate, actually this source position, the center of the source, that will be our center of the coordinate spherical coordinate system. P is a point, it will be characterized by r theta phi. So, P will have a radius r, radius vector r, then theta its angle, and then its azimuth will be phi. Similarly, a current element at a distance z, but with a coordinate dz dash, it will have a radius vector r dashed, that means it is a dashed or primed coordinates, r dashed, angle is theta dashed, and the z coordinate is z dashed. So, with that I can write the what is the current distribution I z dashed, it will be I m some constant into sin beta naught L 2 minus z dash for 0 to L by 2, because current you see for any antenna, the two poles, these two currents, they will be having these differential modes. So, that is why we need to break it into the two poles. So, here it is L 2 minus z dash 2, here it is L 2 plus z dash 2. If you do that, then you see what is the thing at the center, at the center z dash is equal to 0. So, this thing will be maximum here, some depending on the what is the length of the A. So, it is have some non-zero value here, but at the end z dash is equal to L by 2. So, sin 0, that will be 0. So, that is why in both the cases the currents goes to 0 at the ends, and it has some other distribution here sinusoidally distributed. So, once we write this, so then we can have the far field approximation. Now, you see that this distant point P, so that is sufficiently away, that means r is much greater than our z dashed. In that case, the r and r dashed both are parallel, and r and r dashed are almost same. So, they are parallel, and if I very minutely I want to express r dashed I can write as r minus z dashed into cos theta. So, r dashed will be r minus z cos theta. Now, as we have seen that when we will do the superposition, we need these things, and what we will do that we can now write down what will be the far field for each of the current elements. So, for the one shown, that this elemental one, I can write what will be the far field. We know that in the far field we have only theta component of the electric field. So, I can write that due to the dz dashed 1, the d theta component, that will be given by this, just you can refer to your current element derivations. There we have derived that this was the case. I z dash is the current, there is a sin theta variation, there is a 1 by r dash variation e to the power minus j beta naught r dash dz dash. So, this is the current, this is the E field at the point. So, sorry, this is the point. So, at P, this is the d theta and it is oriented in the theta direction and this is the value of this. Now, here you see different points will have different r dash. Now, in the, as we know that in the denominator we can, since P is far away, P is in the far field, r and r dash they are all equal, but we cannot do this here in the phase part, because phase is very much sensitive and actually it is not only r dash, it is beta naught into r dash. So, we know we can take an example that basically let us write this phase term e to the power minus j beta naught r dash. This is actually the angle is beta naught means 2 pi by lambda naught into r dash. So, let us take that suppose this r, this is 1000 meter, let us take r dash is 1000.5 meter, that means only 50 centimeter away another point, and let us say the frequency of operation is 300 megahertz. So, we can find out what is the beta naught r dash value in the first. So, what is beta naught r? If you do beta naught r, because lambda naught for 300 megahertz will be lambda naught is 1 meter and beta naught r, that will be 2 pi by 1 meter into r. So, 2 pi into 1000. So, that will be 360,000 degree, whereas beta naught r dash, that is 2 pi into 1000.5. So, that will be, you see the phase angles, they, though the points are very near, only over a distance of 1 kilometer, they are only 50 centimeter away, but the angle wise, that means when we are calculating phase, they are completely out of phase. So, if we superpose these two, that means if these two phases are added, they will be a null phase or 0 phase. So, that is why we cannot substitute that all r dash are equal here, but we can do this in the amplitude part, because this will come into amplitude part in the denominator we can do. So, here in the phase part, what we will do, r dash, as I said, I can write from the geometry of the thing that is shown here, that what is r dash? R dash is r minus, can write r dash is r minus z dash cos theta. So, that if we substitute in this d, the element, the field due to the elemental current element, then it will be j eta naught beta naught So, total electric field is nothing but superposition of electric field from all the current elements having different ij's, and this will be minus, you can say z dash is equal to minus L by 2 to z dash is equal to plus L by 2, then that d theta okay. So, this if I do this integral, it will be z dash okay. Now, here only thing is it is an integration of dz dash. So, integration variable is z dash. So, this term and this term will be present, all others will go out, and we will have to put the value of this I z dash, the current distribution. So, that we have already earlier written current distribution. Now, we will put that and we will get the value of E theta Now, in the first integral this z dash is negative, this is also negative, we can change these limits, and so the whole thing can be written as this minus sign will come when we will change the limit here, here it will change. So, now this you can note that this is nothing but we can replace this e to the power j theta plus e to the power minus j theta, means a cos term will come extra. So, we can write the total far electric field as j So, this if we integrate, we get beta naught. So, here you see this term is not having any theta variation, all theta variation is here. So, we will be denoting this term, this whole thing, this will be calling a function of theta. So, let me write that theta is cos beta naught L by 2 cos theta minus cos beta naught L by 2 by sin theta. So, thus we can write now what is the far field of a long dipole. It is E theta, that means it is a theta directed field, where what is E theta? E theta is a time phase So, if we put this value eta naught is the intrinsic impedance of free space, which is 120 pi divided by 2 pi. So, this we can write as j 60 Im e to the power minus j beta naught r by r f theta. So, this is we have got the electric field. Now, in the far field we know what will be the magnetic field. The magnetic field will be phi directed, and it is simply in the far field. It will be, we can write it in the similar fashion, is this is the vector term. So, this h phi a phi, and what is this? This is nothing but E theta by eta naught. So, all the theta variation is here. That means, if we want to find what is the pattern, because this is a constant term. So, pattern will be dependent on f theta. Now, this for dipole, actually the length you can choose. So, if we choose a popular choice of length is L is lambda by 2, lambda naught by 2, lambda naught is the wavelength of the operating frequency. So, if we choose that, then it is called a half wave dipole. So, the upper pole is lambda naught by 4, the lower pole is lambda naught by 4, the total length of the antenna dipole, that is half wave. So, it is called half wave dipole. For this half wave dipole, where is our f theta? So, this f theta becomes cos pi by 2 cos theta by sin theta for this half wave dipole. Now, you see that what is the maximum of this f theta, in which direction it is maximum, you can find out that what is the theta in which this is having a maximum, you know how to find maximum. It will be turned out that this theta is 90 degree. That means, what is theta? You look here in this view graph. So, this angle is theta. So, at 90 degree means broadside direction. This is called, in antenna people call it broadside. That means, this is the dipole length, and broadside to that 90 degree to there, this is a maximum. And what is the value of that? Put that this term at 90 degree becomes 0. So, cos 0 is 1 and this is sin 91. So, f theta is 1. That means, the value is f 91. And so, what is the maximum value for half wave dipole? We have already found this E theta thing. Sorry, where is that? This E theta is here. So, if f theta becomes a, so what will be our E max? It is 60 Im by R. So, what is Im? It is the maximum current. So, now let us look at this f theta. If we plot versus theta, we get the pattern. So, if we have a lambda by 2, then for this lambda by 2 things, you see that we have a pattern something similar, and please note that the whole E field expression does not have any variation with phi. That means, in the azimuthal direction it will be a circular pattern. In the elevation pattern we have this for lambda by 2. If we take it L is equal to lambda, the thing is like this. If we take L is equal to 3 by 2 lambda, you will see the pattern will be split in various lobes. There are total 6 lobes in case of this lambda by 2, etc. Now, if we go to the, we will have to calculate that what is the radiation resistance, because we said that a larger antenna will give us larger radiation resistance, and to find that we will have to first find how much power is getting radiated. So, what is the time average power pointing vector? That will be S average, and we know that is half real E theta H phi star in, and it goes in AR. That we have already proved for any antenna this is true. So, here we will be finding that what is this, we have already found E theta and H phi. So, it will turn out to be half E theta square by eta naught AR. So, now if we put the value of this E theta, so this will turn out to be 4.77 Im square by R square f square theta AR. Now, if I want to find out what is the total radiated power, this pointing vector is power density. So, we will have to integrate it over a hypothetical closed spherical surface. So, P R is, we have already seen how to do it. Over an elemental area spherical thing, R square sin theta d theta d phi. So, if I do this, we will get eta naught Im square by 4 pi theta is equal to 0 to pi f square theta sin theta d theta d phi, sin theta d theta d phi already 2 pi that was done, and this is 30 Im square watts. Now, this integral further is not integrable, but so here you will have to put, as we have already seen, the value of your length. So, if we specialize, in some cases it gives a value. So, for half wave dipole, that means if we have L is equal to lambda naught by 2, this integration theta is equal to 0 to pi f square theta sin theta d theta can be integrated, and it becomes value is this. So, if we put that, then PR becomes 36.5 Im square. Now, what was our definition of radiation resistance? The total power radiated is equal to the radiation resistance into the IRMS square. Now, we will have to find out what is the IRMS square. We know for the half wave dipole what is the at the input terminal, that means at the input terminal what was the current. So, that means we will have to put z dash is equal to 0 in either of the expressions of I z dash, and if we do that, you will see that it is basically becoming Im sin beta naught L by 2. So, that is nothing but Im, because this will become a L is lambda naught by 2. So, it will, this is 2 pi by lambda. So, you will see sin pi by 2. So, Im, that means Im is our maximum value, and so what is the RMS value of this? So, IRMS will be Im by root 2. So, that means we can write PR is 73 IRMS square. So, this shows that what is the radiation resistance? Radiation resistance of a half wave dipole is 73 ohm, whereas in previous cases we have seen for current elements it was in, we have calculated various things for various frequencies, it was some milli ohm etc. 73 ohm is quite sizable, that means quite a good amount of radiation is taking place if we take the size to be lambda naught by 2. That is why half wave dipole is quite a good antenna. As far as its radiation, it can radiate good amount of power. We will see what is its other properties in the next class. Thank you.